everyone, welcome to a video on energy changes. The basics behind this video is just looking at whether reactions are what we call endothermic and exothermic. So for chemical reactions to work, bonds have to break in your reactants in order for new bonds to form in the products. Okay, and so molecules come together and they react, and those bonds will break and new bonds form. So if you look at just a single bond, like a chlorine-chlorine bond, in order to break this bond, think about breaking anything. If you want to break a stick, you have to put in your energy, your power, and your force from your muscles to break it, right? Okay, so it takes energy, input of energy, to break a bond. Okay, so to cleave this bond or break it, it takes about 58 kcals per mole. That's the energy. Okay, to form it, however, is the opposite. So to form a bond, this releases energy. Okay, and so when these two chlorines come together, to make a bond here, okay, when the bond forming, then energy is released, and 58 kcals is released because for a chlorine-chlorine bond it took 58 kcals per mole of energy to cleave the bond. Delta H is the symbol that we use to represent what we call the heat of reaction or the enthalpy change. So when I think of H, I think of heat, and so Q is actually our symbol for heat, okay, but delta H is the heat of reaction or enthalpy change, but often reactions either absorb heat or they release heat, and so a lot of times it is heat that we're looking at, but it's called enthalpy, and this is the energy absorbed or released in a reaction. And like I said, a lot of times for chemical reactions, this is heat. That's the form of energy that is being lost or gained. Okay, if in a bond, so right now we're just looking at a single bond. If energy is absorbed, then the reaction is said to be endothermic. Okay, so the breaking of that chlorine-chlorine bond is endothermic because it had to gain energy in order to break. And so we say that this means that delta H is positive. So it gains energy, it's positive, and that means endothermic. We consider that an endothermic process. Okay, when the two chlorines came together, like we showed on the previous slide, okay, this is exothermic because we released energy. So energy is released, think of that as exiting, so it's released, and that means delta H is negative. Okay, and so we can relate this to our what we call bond dissociation energies. In my organic class we call these BDEs for short, and all it is the delta H for breaking a covalent bond by equally dividing the electrons between the two atoms. And so we have lists of bond dissociation energies. You can find those on the internet or in chemistry books or wherever. And these BDE values basically just tell you how strong or how weak the bond is, basically. Okay, so bond dissociation energies are positive values because bond breaking is endothermic. Okay, so that's what BDE means. It's breaking a covalent bond. Okay, so all of these numbers are going to be positive because we now know breaking a bond is inputting energy. We have to input energy in to break a bond. Okay, and then we know that bond formation is negative. Okay, but we're looking more so here. So BDEs are just values we place on different bonds, and it tells us how strong or how weak that bond is. So a hydrogen-hydrogen bond has a BDE of 104 kcals per mole. Okay, so the stronger the bond, the higher the BDE. Okay, so when you compare bonds, okay, from elements in the same group. Bond dissociation energies generally decrease as you go down the column. So if you look here, we have an HF bond, HCl, HBr, HI. So if you look at your periodic table, you're starting up top right, fluorine's our most electronegative atom, and then you're going down. Okay, so as you go down the column, the BDE is decreasing. Okay, so this HF bond has the highest bond dissociation energy, and so it's the strongest bond. Okay, and then comes HCl, HBr, and HI is the weakest of the four that we show here because it has the lowest BDE. Now remember the BDE, okay, if you look back here, all that is the delta H for breaking a covalent bond. Okay, and so if it takes more energy to break a bond, then obviously it's going to be stronger. Okay, so if you think about it that way, HF, okay, has a stronger bond because it takes more energy, 136 kcals versus 103. It takes more energy to break it. Okay, so if I have a little twig, I could easily break it. My child could break it easily. Okay, but if I have a huge limb and I'm trying to break it, it's going to be harder. So I'm going to need more energy, more muscle and power behind it to break it. Okay, and so that means it's stronger. So the stronger, the higher that value, BD value, the stronger, the more energy it takes to break the bond. Okay, if we look at chemical reactions, so we've just been looking mainly at single bonds. Okay, and that's great. And like I said, there's tables that have bond dissociation energy, so you can look at just a single bond and see, you know, how strong a carbon-carbon bond is or a carbon-hydrogen bond. Okay, but now we want to look at a reaction as a whole. So here in this slide, we have methane and oxygen reacts to form CO2 and water. So we have reactants and products. Okay, so obviously we have lots of different bonds here, right? We have 4CH if we drew out all of our. We've got O2, so we've got bonds there. We've got here CO2, so CO2. I'm just doing a few of these. Okay, I'm not drawing the full. Don't want to confuse you, but you've got double bonds. Okay, so we have different bond dissociation energies for all of these bonds for products and for reactants. So we can look at the delta H for the entire reaction, not just a single bond. And this indicates the relative strength of the bonds broken and formed. Okay, so reactants are going to break, then products form. All right, so if delta H is negative for the whole reaction, okay, that means that energy is being released, okay, in forming the bonds. Okay, and so that means if you took all of the BDEs and added them up and got your delta H for your products minus the reactants, okay, you get a negative number. Okay, so in this course we don't go through calculating delta H's for the reactions, okay, but you can do this, but here it's given to you. So it means that heat is being released. Okay, delta H still means enthalpy, but for a chemical reaction, typically this is an energy in the form of heat. Okay, this means that the bonds you formed in your products are stronger than the bonds in the reactants. Okay, and so this is typically favored. Okay, you want your products to be more stable and stronger. Okay, so an exothermic reaction, okay, the products are stronger, the bonds are stronger than the reactants. If delta H is positive, here we have a positive 678, that means that more energy had to be put in to break these bonds, okay, and that means that your reactants, these bonds are stronger. Okay, so this is typically, there's a lot of other factors that play into this, but this is sort of considered to be along with other things like entropy and things we won't go into, but this is more reactant favored if you want to think of it that way, because the reactant bonds are stronger. So a delta H is positive. This is an endothermic reaction. And the reactant side, those bonds, so all the bonds in CO2, okay, and H2O, okay, these are stronger bonds than the bonds over here in the products. Okay, so here's the table that's basically the gist of it all here. For an endothermic reaction, heat is being absorbed or gained, so delta H is positive. And this means that the bonds broken in the reactants are stronger. So, but bonds of the reactants are stronger than the products. So the products are higher in energy than the reactants. Okay, and we want our products to be lower in energy. Okay, they're more stable that way. Okay, exothermic, heat's released, so delta H is negative. The bonds formed in the products are stronger. Therefore, the products are lower in energy. So stronger means lower in energy. Okay, so our products are lower in energy than the reactants. So this is typically more favored as far as forming products, which is what our desire is typically, is to form more products. Okay, so exothermic, release energy, negative delta H, and the products are stronger than the reactants, meaning the products are lower in energy. Okay, and then this is reactant favored. All right, I hope this helps. Thanks.